A very good afternoon, one and all. Thank you for joining with us. Let me introduce myself. I am Dr. Soumya Varghese, Assistant Professor, Department of Chemistry, St. Joseph's College, Devagiri, Calicut. On behalf of Department of Chemistry, St. Joseph's College, Devagiri, Calicut, I extend a very warm and hearty welcome to each one of you present here. Once again, I would like to thank you all for sparing this time from your busy schedules. Before going to the session, first I would like to introduce the faculty members of our department. Dr. Tania Francis, Head of the Department. Dr. Ranjis T. Tom, Dr. Manoj Matthews, Dr. Ranimol Stephen, coordinator of this webinar, Dr. Shinu V.S., Dr. Anish P., Dr. Jomon Matthew, and myself. Speaker, principal, faculty members, please unmute your video so that I can make a click of all of us. Okay. Thank you. This time, we got an energetic young personality as our speaker, Dr. Ramesh Ramapanicker. And the title itself very attractive. Organic chemistry, how much should we mug up? So that we got a very good number of registrations. Actually, we got 345 registrations across the country. Among them, most are graduate students. Usually, students feel difficulty in understanding the topics of organic chemistry. The participation of large number from students' community indicates that they have come up to have some easy tips to mug up organic chemistry. I am sure they will be definitely benefited from this webinar. Once again, I requested all participants to mute your audio and video. Okay, let me move on to the session. First, I would like to call upon Dr. Tania Francis, Head of the Department, welcome address. Tania ma'am, over to you.
Thank you, Soumya. Good afternoon, everybody. It's a pleasure welcoming all the participants to the fourth and final session series of scientific deliberations under the International Webinar Series on Advanced Topics in Chemistry, organized by Chemistry, St. Joseph's College, Devagiri. The major achievements of Devagiri College, as I always say, include gaining of academic autonomy year 2013. It was bestowed with the title Center with Potential for Excellence. It has also achieved NAC double print plus in its third cycle of accreditation with an unimaginable score of 3.76 on a 4-point scale, an NIR of ranking of 60 in the year 2020, and the recently backed DBT star funding of over 1.4 crore. Department of Chemistry is a unique department in that it houses one of the major research centers under the University of Calicut, with all PhD faculty members bringing in funds of over 2 crores from various funding agencies like DST, RUSA, KSCST, and the recently backed DBT Star Fund. We've been seeing a series of webinars during the past month and half. And the first talk in the series was conducted on 9th September with Dr. Sabu Thomas, Honorable Vice Chancellor, MG University, taking us through a journey of 100 years of macromolecules, past and present. On 16th September, we had the second talk in the series with Dr. Shiju N. Ravindran, Associate Professor, Van Hoff Institute of Molecular Sciences, University of Amsterdam, the Netherlands, who has been conducting path-breaking research in the area of catalysis, delivering a talk on catalysis in action, a few short stories. And the third talk was held on 25th September by Dr. Robin Augustin, Senior Postdoctoral Researcher at Qatar University, and he led the deliberations on polymers for tissue engineering and regenerative medicine. Today, we are lucky enough to have with us Dr. Ramesh Ramapanicker, Associate Professor, Department of Chemistry, IIT Kanpur. And he is also going to take us through a more interesting, one of the most interesting, I would say, subjects, which is very close to a chemistry student's heart. Organic chemistry, how much should we mug up? A warm welcome to you, Ramesh sir. Next, I would like to welcome with us our principal, Dr. Sabuki Thomas, who is an ardent researcher and a source of constant support. He is a reputed entomologist and has been a source of encouragement. Welcome to you, sir. I gratefully acknowledge the motivation and support extended to the endeavors of Department of Chemistry by the management of this college. The participation and support received from the student community is commendable, with over 345 registered participants. On behalf of Department of Chemistry, St. Joseph's College, a wholehearted welcome to all the participants. I would like to especially welcome the first year UG and PG students who have joined this webinar. Finally, a request to all the participants to kindly excuse any technical glitches and a reminder to fill out the feedback forms for processing of the e-certificates, which will be communicated towards the end of the talk. With a note of thanks to the coordinators, Dr. Ranimol Stephen and Dr. Soumya Verghese, I once again welcome each one of you on behalf of Department of Chemistry to the fourth talk in the International Webinar Series on Advanced Topics in Chemistry. Thank you.
Thank you, Tania ma'am. Next, I would like to invite Dr. Sabuki Thomas, Principal, St. Joseph's College, Devagiri, to address the webinar. Sabu sir, please.
Very good afternoon. Dear Chief Guest, Professor Ramesh, Ramapanicker, Dr. Rania Francis, the head of the department, and Dr. Soumya, and other faculty members of the department, and the chemistry scholars from different places in and around Calicut, and also could be from other places. And as a principal, it's a pleasure to see the chemistry department, and relate for me also to see the chemistry department is running a webinar series, and they are able to bring in a vast array of topics, plus very well known, international reputed scientists of working in this chemistry field to this particular for the seminar. Okay. So it all, as Dr. Tania was telling, start with Dr. Sabu Thomas. Then came Dr. Shiju Ravindran of University of Amsterdam. Then Dr. Robin Augustin from Qatar University. And I'm a little sad to hear it is ending with Professor Ramesh Ramapanicker, because it could be the end of the series, as she was telling. Okay. So, yeah, it's a pleasure, and as I said, it's a delight for me also, because the young minds of the Devagiri College, I know that all of them are attending it. We attract the best in the region with our A++ status and all. We get very good students for all streams of science, and specifically for chemistry also. So definitely there is a very good young audience keen to listen to Professor Ramesh Panicker. I'm extremely happy to tell you that. And they will be quite thankful to you also, because they're all getting an opportunity to listen to people like you. And I can assure you, your precious time, it will not be wasted. And the students will be keenly listening to you, and they will be getting ideas, and then they will be able to plan their future. So thank you very much for accepting the invitation from the department, and kind enough to spare your precious time for this Arts and Science College students, the program of the school, so organized by this college. Thank you. Yeah, it stopped, Dr. Soumya, please continue.
Okay, sir. Okay, thank you, Sabu sir, for your inspiring words. Next, I would like to call upon Dr. Shinu VS to introduce the speaker. Dr. Shinu sir, over to you.
Okay. Can you hear me? Can you hear me?
Yes, you are audible.
So today, for the fourth lecture in the international webinar series on advanced topics in chemistry, we have another eminent personality in the field of organic chemistry, Dr. Ramesh Ramapanicker, Associate Professor, Department of Chemistry, IIT Kanpur. About Dr. Ramesh Ramapanicker. Dr. Ramesh did his post-graduation in organic chemistry from the School of Chemical Sciences, MG University in 2001. After his post-graduation, he joined IAC Bangalore for a PhD degree, and where he worked on the chemistry of carbamides and carbonates under the guidance of Professor S. Chandrasekhar. After obtaining the PhD degree in 2007, he moved to Uppsala University, Sweden for postdoctoral research, and he worked with Professor Dar Balser on the synthesis of design peptides for protein binding. After his postdoctoral research with Professor Balser for a period of about 3 years, he joined IIT Kanpur in 2010, where at present he is an associate professor of chemistry. To his credit, Dr. Ramesh is an author of a large number of articles in peer-reviewed international journals of organic chemistry. His research interests include synthetic organic chemistry, asymmetric synthesis, and peptide design. Today, he will be speaking on the topic organic chemistry. How much should we multiply? With these few words, I welcome you, Dr. Ramesh Ramapanicker, sir, for your talk.
Thank you very much. So I'll start sharing my slides now. Okay. Good afternoon, everyone. I am very thankful to Devagiri College and the coordinators of this symposium for inviting me to present a seminar today to the students of Devagiri College in particular, and also to many other students from other colleges and universities, as I understand. I thank Dr. Ranimol Stephen, first of all, because she was the one who contacted me, and also Dr. Soumya Varghese, for organizing this webinar series. And from the list of speakers and the topics that have already been covered, I understand that it was quite an engaging webinar series that you are having. I thank Dr. Sabuke Thomas, the principal, for supporting the chemistry department in carrying out this kind of a webinar series and other academic activities. Now, Devagiri College is very close to my heart in the sense that I knew about Devagiri College for the last 22 years probably. It's because I have some of my very close friends who have studied in Devagiri College, who continue to be my friends. And currently I have very close friends who are faculty in Devagiri College. Dr. Renjisti Tom was a very close friend, is a very close friend of mine. We were together during our MSc. So it is always a pleasure to be talking in front of the faculty and students of Devagiri College. When I was contacted to give a lecture in this webinar series, Ranimol gave me two options. So one of them was either to talk about my research or to talk about something that would help students understand organic chemistry, learn organic chemistry better for competitive examinations. This is what he told me. I understand that it is a big issue because normally what happens in most of the competitive examinations, students who do well in organic chemistry are the ones who score well. And so if you ask people who qualify CSIR exams or GATE exams, most of them would tell that they had a fair share of answers correct in organic chemistry. So therefore, if it happens to some of the students that they find organic chemistry difficult, then they would probably score in many of these competitive exams quite poorly. So I thought I would rather talk on a topic that deals with organic chemistry in general. And the reason is this. So if I have to talk about my research, I personally prefer it to be on a seminar where I can see the people whom I am talking to, so that I can understand how much I'm engaging the audience and probably how much they understand or they value the research that I do. So therefore, I can tune my talk accordingly. While I'm talking onto a screen as I'm doing now, it makes much of a sense to be talking about organic chemistry in general, which is the closest thing to my heart, and which is why most of the people are attending this seminar, because organic chemistry is close to them. So I thought of taking up this, putting up this title, Organic Chemistry, How Much Should We Mug Up? Because right from the time I started learning organic chemistry as a subject, that is in my 11th and 12th, I've always been hearing that organic chemistry is all about mugging up a few things. And if you're good in mugging up, you score well. And those who do well in organic chemistry are the people who know a lot of things by heart. So what I did while preparing for this lecture, I just had a Google search on the name reactions that students of 11th and 12th standard learn. So I came up with a list of 30 reactions. There are more, but 30 important reactions that are listed here. So what it tells is, if you want to do organic chemistry well up to the level of 11th and 12th, you probably have to learn these 30 reactions by heart, the reagents used in them, the substrates that are reacting in these reactions, and so on. If any of you go through this list, it is actually quite intimidating, and not all reactions are very easy. Some of them are very common, like Grignard synthesis, for example. But there are others which are not so trivial or which are not so easy and which are extremely difficult to remember. So a student who does well in organic chemistry in 11th and 12th has probably by-hearted all these name reactions. They know all these name reactions by heart. Some of them have by-hearted them, some of them have learned them by understanding the reactions a little better. In the end, everybody has mugged this up. So then when I thought, because I know this, I would also have a look at what are the formulae that physical chemists would learn while learning 11th and 12th, or the formula in physical chemistry that is used for 11th and 12th chemistry. So while I searched that, I was not daring enough to list those, but I found that the list is even bigger. There are more than 30 for sure, the number of equations and number of formulae that you learn in physical chemistry. And a large number of constants too. But in many exams, the constants are given, so it helps. But however, there are a large number of equations. And you need to remember these equations if you want to do well in physical chemistry. As in the case of organic chemistry, you need to remember these 30 reactions or more, a little more. But in physical chemistry, you have a large number of equations to remember. Then the question is, why does organic chemistry get all the blame? So you learn in physical chemistry, you learn in organic chemistry, you learn in maths, you learn in physics, and in everything you remember equations. And in organic chemistry, you remember reactions. But organic chemistry is the one that is always being discussed as the topic that requires by-hearting or mugging up. Now, to go further, what I did, I put these subjects, which when a student passes from 10th and start taking +2, the subjects that they learn are maths, physics, chemistry, and biology. And I put them in this order for a reason. So if you look at the extreme left side of mine, you would see maths is a quantitative science, whereas biology is qualitative. What I mean by this is maths is based on equations. So if you know one equation, you can derive it into other equations. And most of the equations and most of the formula you can relate. So it is quantitative. You can build on them and you can learn it completely. But by the time you reach biology, it is all about names. It is all about things that you need to remember. But nobody tells a biology student that you have mugged up things. In fact, if you want to learn biology, you should by heart. There is no other way that biology can be learned. People learn about different kinds of flowers, different kinds of leaf forms and everything. And all of this requires that you learn the names and remember them. And physics and chemistry come in between. So while you move from maths to physics, you will find that the extent that you need to remember increases. And by the time you reach chemistry, it is little more. And once you are in biology, it is almost entirely remembering the things that you have read. Now, again, chemistry again split into two. So one of them is theoretical chemistry and another is organic chemistry, whereas experimental physical chemistry and inorganic chemistry would probably come somewhere in the middle. Theoretical chemistry is more close to physics or maths, or theoretical physics or maths, and whereas organic chemistry is closer to biology. And in theoretical chemistry, you learn equations and which are derived, whereas in organic chemistry, again, you are going to learn a lot of reactions that you by heart, just like you did in biology. So this is what happens. Now, this is an image that people get even when the public understanding of a mathematician, a physicist, or an organic chemist is such that somebody who does mathematics, a mathematician would be somebody who is freaky, who is nerd, who probably does not take care of himself, but is completely involved in deriving things. And so is the case with physics. And by the time you reach organic chemistry, you start seeing people who are well-groomed and so on. So just to explain this point further, what they did, I have taken photographs of a few TV shows or films where these class of people are represented. So all of you would know. So if you look at the first person here, that means, one second, let me just have my laser pointer activated. Okay. So if you see here, this person here, this is Russell Crowe acting as Dr. Nash in the film The Beautiful Mind, where he is a Nobel laureate who has got Nobel Prize, and he is a mathematician. You look at him, he is actually not interested in the worldly pleasures. It is very clear from the face. And that is how eccentric mathematicians are represented in popular media. And then in the middle, I have Sheldon Cooper, one of the characters whom I like the most. He is from Big Bang Theory. And you can see that he looks right through you. He looks into your eyes and he probably sees what you have in your brain. And he doesn't care how he looks. And he's an eccentric person. Whereas on the extreme right side, whom I have is Imran Hashmi from the movie The Body, where he's an organic chemist. And just to show that he's an organic chemist, I'm not sure how many of you can see this. There is a whiteboard behind him, and there are some organic chemistry structures. So if you look at the structure that is shown here, it is a structure of proline, and the structure is wrong in this one. So proline is actually a 5-membered ring where there are 5 atoms in the ring, but here you can see that it is a 6-membered ring. And so the structure of proline is wrong, but nobody cared about it. So I'm not sure who was the organic chemist whom they contacted to get this board written. But anyway, it is wrong. But you can see among all this particular person seems to be taking care of himself better. And he is probably the most well-groomed one. So this is the idea. So organic chemistry is always about not being so eccentric, but about mugging up things. Now, then the next question is, so I would agree that organic chemistry means you need to remember. Then the question is, how much would you remember? So I have a few questions for all the people who are attending this one. So if you read through my questions, do you know the smell of flowers? So if I show you a flower, for example, a rose, and ask you how does it smell? You would immediately, most of you would associate a smell with rose. Or in the other hand, if you walk into a room, whether a perfume with rose smell has been sprayed upon, you will immediately realize, okay, this room smells like rose or this room smells like jasmine. This is because you know the smell of jasmine or rose and you have remembered them. Similarly, all of your colleagues, if you are a student, you have classmates. So some of you would know that as soon as the class starts, you join a class, you have 40 classmates, and within a week, some of you would know the names of all the 40 students in the class. Some of you are not so good. You might probably take even 6 months to know everybody by their name. So the person who knows the name of all your colleagues or all your classmates, he has remembered their names, but nobody tells him that you actually mugged up the names. We would be happy that, oh, he has such a rare talent that anybody whom he meets once, he remembers their name, he remembers everything about that person. Now imagine I bring up a person and tell that this particular person is so talented that he can identify 100 flowers by their smells. You do not call him a person as somebody who has mugged up the smell of the flowers. You would call him as a person who knows these flowers so well that he can associate a smell with a particular flower. But then it comes to organic chemistry. The question is, do you know the structure of 100 organic compounds? So you can list a large number of organic compounds. You can start with benzene, you can go to cyclohexane, you have toluene, xylene, phenol, and so on. So there are a large number of organic compounds. So if you hear the name of an organic compound, can you associate a structure with that? Now, if you know 100 organic compounds along with their structures, have you really mugged them up, or do you consider it as knowing those molecules close to your heart? Now, the next question is, do you know 30 organic reactions by name so that you can pass +2 or you can pass an entrance exam by scoring high in organic chemistry? So along these 4 questions, you will suddenly start to realize that at certain point, knowing and understanding or knowing closely has changed into by hearting. Now, then why is organic chemistry getting a blame when 30 reactions has to be remembered, whereas knowing the smell of flowers never gets a blame for by hearting? So I can tell you this: when you take a flower and start smelling it and remembering its smell, it is your choice. You can either do it or you can not do it. That is up to you. Whereas when you are asked to learn 30 names of organic reactions, you have no choice, because you are going to be examined. You will be writing an exam where these organic reactions will be listed out to you, and you will have to understand them and probably write an answer based on your memory. So the last one is not a choice. It is something that everybody is supposed to do as long as you are taking science stream and learning chemistry. So that is where you have a problem. Now, physical chemistry required that you learn some formulae. Now, so a person who knows all the formulae in physical chemistry, if you are asked to tell me one favorite formula, you would probably tell me one, but you just tell it from your memory, but you do not associate any picture along with it. Whereas when it comes to organic reactions, you always have a picture of an organic reaction. So if it is Friedel-Crafts alkylation, for example, you would immediately have in your mind the picture of a benzene ring that is probably going to react with a cation. And so therefore, organic chemistry requires that it is more qualitative in nature. So what you remember or what you study by heart is more related to the smell of a flower. Smell of a flower is its quality. Similarly, organic compounds are qualitative. So if you would like to remember them, you have to remember them, and it is very difficult for you to tell somebody else what exactly are you remembering. Just like the smell of a flower. You cannot go and tell another person that the smell of jasmine is this, unless you have a jasmine flower with you. So that is the same thing here. So there is a different level of learning that is required for organic chemistry and physical chemistry. So a person who does well in physical chemistry need not do well in organic chemistry. And similarly, a person who does well in organic chemistry need not do well in physical chemistry. Because these two require two character types. Just like one of your classmates is able to remember the name of all your colleagues within 2 days, whereas you might take 6 months to learn all of their names. So it is remembering, it is by hearting, it is mugging up, but the nature of by hearting or the nature of remembering is different, because one of the sciences, organic chemistry, is qualitative, whereas maths, physics, and theoretical or physical chemistry is more quantitative. Now, before I go further, anything more I do with organic chemistry and organic compounds, it is important that I start discussing the geometry of organic compounds. So let me start off by telling you that organic chemistry is extremely simple, because it is all about carbon atom. And carbon is such a guy that it has an electronegativity or an electropositivity which stays somewhere in the middle. So it very rarely stays as a positively charged species or a negatively charged species. So it is always uncharged, and in most cases it has 4 bonds, and either it is an sp3 hybridized carbon atom where it has no double bonds. So if it has no double bonds, what you would see is that it takes a tetrahedral structure, and if it is sp2 hybridized, it takes a planar structure where you have 1 double bond, and it can be sp hybridized where you have a triple bond, as you can see here, or 2 double bonds. So if a carbon atom is directly attached to 2 double bonds, then again it is sp hybridized. The linear structure of an sp hybridized carbon atom is very easy to understand. It is just linear. It is like a line. And a planar structure again is very easy to understand. It is on a plane. Whereas once it comes to a tetrahedral structure, this is the structure that is probably the most difficult to comprehend. Not all people would be able to see a tetrahedral structure standing in the space just in front of your eyes, because it is an extremely difficult concept. So I have a tetrahedron here. So what I have, these black balls on all these places, all these corners. So these are the hydrogen atoms. So now I have a rather X-ray of this thing, and the one in the middle, exactly in the center of this three-dimensional structure, is the carbon atom. So a tetrahedral carbon atom has to be viewed like this, where you have the carbon atom in the center and all the hydrogen atoms on all these corners. Now, when you start doing organic chemistry, the important thing is you should be able to draw a tetrahedral carbon atom properly. There is absolutely no difficulty in drawing a planar carbon atom or a linear carbon atom. But once you start drawing a tetrahedral carbon atom, it becomes a little bit difficult. Now, a tetrahedral carbon atom can easily be drawn like this. First of all, you draw two lines like this, and preferably the bond angle between them has to be 109 degrees. And once you have drawn them like this, that means with these straight lines, what you really mean here is that these two bonds are on the plane of the screen here. So that means they are exactly lying on the screen. And then I have a solid line that is drawn like this, and then I have a dashed line like this. So this solid line is sometimes called as a wedge. So this is as if this bond is coming towards you. So if you look at the screen, these two bonds, which are drawn simply as lines, they are on the plane of this screen, and this one is coming towards you and this one is going away from you. I can rotate this and draw them in all these ways. So all this actually means that you have drawn a proper tetrahedron. Now, while you do this, so effectively what you need to draw is draw two lines which are on the plane of the screen, then one line as if it is pointed towards you and another line as if it is pointed away from you. Now, the angle between each of these lines, each of these bonds are going to be 109 degrees. Now, if you can see this particular species in front of you in the air, standing in space, that means you can understand a tetrahedral structure better. But while drawing, most of the students especially make this mistake. They draw these two lines like this. So please follow my pointer here. So you draw two lines on the screen. Then you put one of these bonds pointing towards you and another going away from you. But the bond that is going away from you is happened to be between these two lines which are on the screen. So if you draw a structure like this, or if you draw a structure like this, where the bond towards you is between these two lines, then these are not tetrahedral structures. And if you draw them like that, while writing an organic reaction, for example, you would end up drawing a wrong structure, because if you draw like this, there is no way that you can have a tetrahedral structure in space in front of you. So this is actually a very skewed structure where the tetrahedron has been compromised. For those who are interested in organic chemistry, I understand that not all of you would be following organic chemistry so closely. So these three things I have drawn here, just to tell you that if you draw the lines the way I have drawn here, then you would get the configuration of the tetrahedral carbon atoms wrong. So you can see that in two of them, it goes in a clockwise fashion. Then I go from 1 to 2 to 3. Whereas in the third one, it goes in an anti-clockwise fashion. So if I assign the configuration of R and S to these molecules, although they are the same molecule, you would end up getting a wrong configuration for this. So that tells you that you can never draw a tetrahedron this way. Now, the other thing is that the structures need not always contain two bonds on the plane of the bond. The tetrahedron can also be drawn in any of these ways. But then it all comes to viewing this structure more clearly. So now, why did I tell you this? Is rather than remembering all the organic chemistry that you have remembered, all the named reactions that you have remembered, seeing a tetrahedral carbon atom in space is more important. Now, many of you have gotten through to organic chemistry. Many of you have taken BSc chemistry or MSc chemistry because you did well in your +2. You liked chemistry because you could remember all those reactions. But then suddenly you start to realize that organic chemistry is getting tougher and tougher for some of you. But for some of them, it becomes easier. Now, why is it becoming difficult is that suddenly mugging up stops helping you. Even when you know the structures, even when you know the reactions, you are not able to write all examples properly. And that is because you are failing with the three-dimensional structure of organic molecules. So being able to view a structure in 3 dimensions becomes extremely important if you would like to take organic chemistry as a career. I will go further because I realize that I'm taking up more time on those points. So let me tell you this. Now, once you come to organic reactions, what are organic reactions? So every organic reaction is a reaction between a nucleophile and an electrophile, or it is a reaction between an acid and a base, or it is a reaction between a positive charge and a negative charge. You know, a nucleophile is something that is electron rich, and an electrophile is something that is electron deficient. An acid, a Lewis acid, is something that is electron deficient, and a base is Lewis base is something that is electron rich. A positive charge is electron deficient, a negative charge is electron rich. So that simply means all these 3 sentences I have written here have the same meaning. Now, whenever you look at any organic reaction, no matter what name you have given to the reaction, the reactions are effectively going to be between a nucleophile and an electrophile. It is going to be a positively charged species and a negatively charged species. It is going to be between an electron-rich species and an electron-deficient species. So start looking at organic reactions this way, then you will be able to start writing mechanisms clearly by yourselves. So I've taken these examples here. So this is one of the reactions that you learn very early when you're doing your 12th standard chemistry. So you learn nucleophilic substitution reactions when you learn alkyl halides in 12th standard. So this is the first organic chemistry chapter in 12th standard NCERT book. You start with an alkyl halide, so that means the next is a halogen atom like chloride, iodide or bromine. And then when it is treated with a nucleophile simply is any species that has a negative charge. You end up getting a reaction like this where the halogen atom, the X, is replaced as an X minus, and the nucleophile with its negative charge has now gotten bonded here. So this is what it means. It means there is a substitution of X with Nu. So this is a very simple reaction. All of you know this. This reaction happens in 2 different ways. One of them is SN2 reactions, where the nucleophile attacks and the X goes in such a way that at some point the carbon atom is attached to both the nucleophile and the X together. And as the X starts to leave, this bond between the nucleophile and the carbon atom start becoming stronger and stronger. And while this pink bond becomes stronger, the green bond becomes weaker. And at the end of the reaction, you have a nucleophile attached to the carbon atom and the X has completely left the carbon atom. So this is a substitution. And this reaction is called SN2 because both these species, that is the nucleophile and this alkyl halide, are together involved right from the beginning of the reaction. So the 2 stands here for bimolecular. That means the reaction uses both the molecules to start the reaction. And the second one is an SN1 reaction, where when the reaction starts, only one of the species, that is the alkyl halide, is present. So this guy, the alkyl halide, just gets dissociated without even the nucleophile approaching it and gives you a positively charged carbon atom, which is sometimes called as a carbocation. The more correct term is a carbenium ion, but you can call it as a carbocation, which means it is a cation having a carbon atom. So a carbocation here, and the X minus, which is the halide that has come out. This is a very slow process. So if this can happen faster, then a nucleophilic substitution of this kind takes place. And once you have gotten the positively charged species, then this one reacts with the nucleophile and gives you the substituted product. So in one of them, both the species, that is the nucleophile and the alkyl halide, are present in the reaction right from the beginning. There are no intermediates. Instead, you have a transition state which looks like this. And finally, you have 2 products. One is X minus and another is the substituted organic compound. And in SN1 reactions, in the beginning, you have a first step where you generate a carbocation and an X minus. And then you have a second step where the carbocation reacts with the nucleophile. Now, what is interesting about this SN1 and SN2 reactions is it follows some stereochemistry. That means you look at this molecule here. Those who know configurations can assign this as this with an S configuration. You can see a bromide here. And what happens in the first step, like I told before, the Br goes out, gives you a Br minus. That is what happens in an SN1 reaction. And what we get here is a planar compound, which is sp2 hybridized, and this is the carbocation. And the positive charge simply means there is an absence of electrons in one of the orbitals, which is represented as a p orbital here. Now a nucleophile, here I have chosen an alcohol as the nucleophile. The nucleophile then adds on to this p orbital. The nucleophile can come from the top and interact here, or it can come from the bottom and interact here. If the nucleophile comes from the bottom, then I get this molecule, which has the OR group, the H goes away, which has this OR group, which is downward. And if the nucleophile comes from the top, then I have this OR group, which is from the top. Now, if you look at your starting material and this compound here, you would see that Br is exactly replaced with an OR. The molecule has retained its configuration. That means from where Br has gone, an OR has added. So you can say that this particular compound is formed with a retention of configuration, whereas this one has resulted in an inversion of configuration. That means the Br went away and your OR group is now pointing downwards. This is because the RO group attached from the lower lobe of this orbital. So this makes perfect sense. So therefore, what would happen in this reaction is, if you do this reaction, both these things would happen with the same probability, and you would get a mixture of products where you have 50% of this and 50% of this. That means when you started with an optically pure compound with S configuration, your product has two configurations, both S and R, and you have got a racemic mixture of compounds. So you could say that it has led to racemization. Now, one second here. I'm sorry. Okay, so now while we are talking about the stability of carbocations here, so we have talked about carbocations. So let me go one step behind. I just got lost a little bit in between. I'm sorry for that. So when you take this intermediate here, you can clearly see that the intermediate here is a carbocation. So let us have a look at the carbocation in detail. So what you have here is a carbon atom that has 3 bonds, which you can see, and an empty p orbital. Now, we also say that the stability of carbocations go in this order, that tertiary carbocations are more stable, secondary less stable, and methyl is the least stable. What it simply means is the stability of a carbocation is directly related to the number of alkyl groups attached to them. So I can show it clearly here. If the p orbital is adjacent to a carbon atom that has another bond, such as a CH bond here, then this orbital, which happens to be the bonding orbital of this carbon hydrogen, has 2 electrons. So 1 electron from carbon, 1 electron from hydrogen. This orbital and this orbital are fairly closer, so they can start to interact with each other and stabilize this empty orbital. So whenever you have an empty orbital, if you have a filled orbital such as this CH bond closer to it, and if it is parallel, then they can have an interaction, and that interaction is what we normally call as hyperconjugation, and that would stabilize this. So therefore, once you have more number of alkyl groups around the positively charged carbon atom, that means this is a CH3, if you assume this is a CH3 and this is a CH3, the number of such interactions are more, which would stabilize the carbocation. Another way of stabilizing the carbocation is if you have a double bond or if you have a phenyl ring closer to the carbocation. So I have written the carbocation here. It has a double bond. Then what would happen is this electrons in the double bond can be donated onto this carbocation, forming a new double bond. And the positive charge here has changed onto this carbon atom, because the double bond means 2 electrons, and those 2 electrons are now going to be between these 2 carbon atoms, and it has resulted in a new double bond and also a positive charge on one of these carbon atoms. Similarly, a phenyl ring can also do this. So these 2 slides would actually tell you that a carbocation, which is an intermediate that you get in an SN1 reaction, will be stabilized if you have tertiary groups, tertiary carbocations, or if you have a double bond or a phenyl ring closer to the carbon bearing the positive charge. Now, when I say this, it makes all sense. But now the question is, I would also like to put another set of structures here. So if you have a look at this particular structure here, this is almost the same thing, except that I have rotated this single bond such a way that, so in this structure, what I mean is one of the bond is coming towards me, another bond is going away. Whereas in this, all of them are on the plane of the screen. So when I have drawn the same molecules here, and all I did here is that before the double bond comes onto this, I have just twisted this. Now, let me ask you the question, all of you to answer yourself. Which of these sets are actually correct? So if you see, this is another representation of this, where I have rotated this bond and drawn this like this. So those of you know organic chemistry closer would realize that this is the correct way of drawing it. This is wrong. It is just because the p orbital on this one can interact with this double bond only if all these bonds are in one plane as I have drawn here. So if this group is pointing towards me and this group is pointing away from me, that means that my p orbital is on the screen, whereas the p orbitals on the pi orbitals on the double bond are actually not on the screen. They are perpendicular to the screen. Whereas in this structure, the p orbital is also perpendicular to the screen. The pi electrons in this double bond are also perpendicular to the screen. And only when they both have the same orientation, they can interact. So therefore, what I could say is this structure which I had on the left side is wrong. I can only draw a mechanism or a stabilization correctly if I do this. And now to understand this, what I needed to know is how the atoms actually occupy space and how my orbitals are occupying the space. Now I'll move on to SN2 reactions. We see that in SN2, so remember that in an SN1 reaction, you got both the products. That means if you started with S configuration, you had R and S products. Whereas if you do an SN2 reaction where the nucleophile starts to attack along with the leaving of the carbon X bond, then you always get an inversion in configuration. You do not get a racemization. You get only one product where the nucleophile will be added to the carbon atom in such a way that the carbon is flipping out. So if you look at all these three bonds here and consider this to be an umbrella, while the nucleophile forms this bond, all these three bonds are flipped over, just like your umbrella would do while it is in a windy situation. So this has resulted in an inversion of an umbrella or inversion of the carbon atom, giving you this structure. There is a reason why this happens. Here the nucleophile starts to react before the carbon X bond has left. Now, how do an organic chemist explain this? We simply say that when you have a carbon X bond, the anti-bonding orbital of the carbon atom, carbon X bond, is oriented opposite to the CX bond in this direction, and the nucleophile donates its electrons to the anti-bonding orbital. An organic chemist does not tell you what exactly is an anti-bonding orbital or which molecular orbitals are we talking about. We simply say that a carbon X bond has orbitals. It has a bonding orbital which has electrons between the carbon and X. It has an anti-bonding orbital which is away from the carbon X bond, and the nucleophile starts to donate electrons to that. And when the nucleophile starts to donate electrons to that, the bond order from the CX bond finally becomes zero, which would result in the CX bond to leave and start giving you this. So this is how an SN2 reaction can be explained better. So ultimately, the reaction would result in an inversion of configuration. So then the question is, so I talked about hybridization. I talked about sp3 hybridized orbitals. I talked about orbitals, anti-bonding orbitals and bonding orbitals. So then the question to an organic chemist is, so you are talking about orbitals. So which orbital theory are you following? Are you following valence bond theory and hybridization? Or are you following molecular orbital theory and bonding and anti-bonding orbitals? So whenever a theoretical chemist talks to an organic chemist, the theoretical chemists start to flip out because the organic chemists would start mixing up molecular orbitals with hybridization, molecular orbitals with sp3 hybridized orbitals and their shapes. We would talk about bond angles as if it is entirely valence bond theory, we will talk about VSCPR repulsions, and we will talk about everything. So it is a mixture of everything. So this is where an organic chemist starts to get messy. Now, is an organic chemist right in doing this? Or is a theoretical chemist right in finding fault with an organic chemist for using these theories mixed? Now, the answer is, what are you going to do with your organic chemistry? Are you going to look at reactions, and are you going to explain them better? And if your entire effort is explaining an organic reaction, whichever orbital theory helps you at that moment can be used. All my theoretical chemistry friends here in the Department of Chemistry at IIT Kanpur, they tell me that hybridization does not exist. There is no hybridization. I say, I know. Hybridization is an outdated theory which probably should not be used unless you are doing organic chemistry. Because as an organic chemist, I am more worried about explaining about the reactions I see. So I use an outdated theory because it helps me to explain what I see and what I do. If the physical chemist or a theoretical chemist or a theoretical physicist can come up with another theory that can help me in solving my organic reactions better, I am ready to replace orbital theory, valence bond theory, and hybridization. But until I do not have such a theory available to me, and until molecular orbital theory with all its complications appear to be complex, I'm not going to use it. So what I really use is, I will use the term antibonding orbital, and I will still use it as a hybridized orbital, because using molecular orbitals with a local understanding of each carbon individually helps an organic chemist. So it is okay to mix up theories, provided your purpose is to explain your observations better. I'll come to that later. So quickly, I will go through a radical reaction. This is just to tell you that when I told you that all the organic reactions are nucleophilic reactions and electrophilic reactions, all the reactions mean that a positive charge will react with a negative charge. Obviously, some of the students would have this doubt, what about radical reactions? In radical reactions, there are two radicals which are reacting with each other. There is no positive or negative charge. So let me just briefly go through this example. So this is an alkyl iodide reacting with an alkene, which results in the formation of an addition product such as this. So you can see that the R group just added across this double bond, the iodide completely went away, and you have a product such as this. So just to explain this to those who are interested in organic chemistry, AIBN actually means this, which is asa bis isobutyronitrile. So those who do not understand this, just leave it aside for now. So it simply means that this is a compound such as this. It has a nitrogen-nitrogen double bond. So if you heat this compound is quite unstable. So therefore, what will happen is a nitrogen molecule would just get liberated. And while it is doing so, it will give me two radicals. And radicals simply mean these are carbon atoms with one unpaired electron in each of them. Now, once I have these two radicals available to me, what this radical does is, so by ABN, I mean this one here. So once this radical is formed, so what this radical would do, H from this BU3SNH. So this BU3SNH here is tributyl tin hydride. So this radical takes away this H, and then it gives me a new radical, which is BU3SN dot, where SN stands for tin. So now what would this radical do? It will take an I from here, from iodide from here, and BU3SNI would come out, and the alkyl iodide has become an alkyl radical. This alkyl radical would react with this alkene and generate a new radical here, and then this radical would take this one H from BU3SNH and give me this product. And once an H is lost from here, you get back this. So this is a slightly complex mechanisms for those who are not used to it. But just look at the points that I am trying to tell you here. So the R dot is a radical. This radical reacted with this alkene, and that is when I get this product. So I get this radical first. Now the product I get from this reaction is also a radical. But this radical did not go back and react with another of this. Instead, what this radical did, this radical just abstracted a hydrogen from here and gave me this product instead of reacting with an alkene, just like the R radical did. Now, this reaction never happens in that direction. And if the radical here started to react here, then I would get a very complex reaction mixture, and this whole reaction will not yield anything. Now, if you understand that an alkyl radical is electron rich and this double bond is electron deficient because of the cyano group, that is the reason why this R adds on to this. And that is the reason why I get this radical. Now, this radical, where the carbon atom having this electron is closer to a cyano group, so this is electron deficient. Because this is electron deficient, it cannot react with this alkene because the alkene is also electron deficient. So the only thing it can do, it can take an H from this and give me this product. So the entire reactivity here, although it is radical based, is controlled by the fact that some of the radicals are electron rich and some of the compounds are electron deficient. So the whole reaction is again between an electron rich species and an electron deficient species. So the things which I said earlier about organic reactions, that organic reactions are between electron rich species and electron deficient species, still holds true, even for radical reactions. So you will understand this if you follow this particular point here. Okay, now, so we take these things for granted. We have learned the structure of a tetrahedral carbon atom. We know what it means. We have decided to use orbitals the way we like. We are assuming that every carbon atom, no matter what, is hybridized, and the hybridization is sp3 for a saturated carbon atom, sp2 if it has a positive charge or if it has a double bond, and sp if it has a triple bond. We can do complex structures, and all the structures have to be viewed in space, and we should be able to see this. If you know this much, then let us look at this molecule here. This is camphor, and this molecule here is camphor sulfonic acid. So the only difference between this compound here and this compound here is a sulfonic acid group attached to this CH3. Now, if you are an organic chemist, a starting organic chemist, and I start asking you, how will you do this? If we have learned about nucleophilic substitution and other reaction, but there is no way that you can take a CH3 and start replacing one of the H with a sulfonic acid group. It is not very easy. So an organic chemist would get stuck here. None of the name reactions that you have learned, you have by-hearted, are going to help you here, because this is a new reaction. Now, this reaction can very easily be done. How would you do that? All you need to do is take camphor, treat it with acetic anhydride in the presence of concentrated H2SO4. This is the product. Now, if you look at the number of methyl groups here, there is one here, there is one here, there is one here. But the SO3H specifically goes to this carbon atom. It does not go to this methyl, it does not go to this methyl. Now, if I am a theoretical chemist, if I am a theoretical physicist, I would see somebody did this reaction, they got this product. Now you have to explain why this happened. Now, if I'm starting to explain why this happened, I can use theory from first principles and start solving this. Those who are currently doing MSc would know that you are solving particle in a box. You are solving particle in a three-dimensional box. You are solving hydrogen atom with one electron, and everything is so much of derivation. Now, if you would like to derive this particular reaction and come up with a reason why this product formed, you would spend your entire life only in this particular reaction and still will not get a theory that can completely tell you from first principle why this reaction happened. Chemists look at this reaction, gives you the mechanism. So this is the mechanism. It is by no means a simple mechanism, but this is what really happened. When I just took camphor and added two reagents to this, acetic anhydride and concentrated sulfuric acid, I got camphor sulfonic acid, which is a result of everything that is in this slide. Now, it looks extremely complex. Somebody who is not doing organic chemistry, this is the time you sign out from the meeting and go off, because this looks and makes no sense to you. But I told you that as an organic chemist, I remember only a few things. I look at a carbon atom as a tetrahedron. I try to see in which direction the orbitals are oriented. I know that a positively charged compound, a positively charged species would always try to react with a negatively charged species. So I take this compound, which is camphor. I treat it with an acid. That means I have an H+. The H+ in this molecule finds the most electron-rich species, which in this case is this oxygen, because it has lone pairs of electrons. So then what happens? I get a positively charged oxygen here. I get a protonated carbonyl group with oxygen having a positive charge, because oxygen gave its lone pairs to the H+. So this is the electron-rich species. So the H+ has gone and reacted with it. Now, the moment this happens, this carbon atom is now starting to feel a positive charge. One of the things that I can do, I can draw an arrow like this and put this double bond onto the oxygen atom so that the oxygen has only 2 bonds, and then the carbon will have a positive charge. A positive charge in a carbon means carbocations, which we were talking about. That means that this particular carbon atom here has a p orbital, and that p orbital is oriented parallel to this bond here. So if you look at my laser pointer here, you would see that I am moving it through a bond, and that bond and the p orbital that is going to form on this carbon atom are parallel to each other. So therefore, this bond here is now going to migrate or donate its electrons. So this bond is going to break, and the electrons in this bond are going to be donated to this carbon atom. And then I get a new species like this. This looks different, but let us have a look at this. The positive charge is on the carbon atom, that is this. This bond is broken, so therefore I do not have a bond between this carbon atom and this carbon atom. So there was a bond like this before, it is gone. There is a new bond between this carbon, and this is the new bond. The electrons went away onto oxygen, so I have an OH. So because this bond broke, this carbon atom now has a positive charge. So I get a new species. So I get a new carbocation. So now this carbocation is sp2 hybridized. Every carbocation is sp2 hybridized for me. And this sp2 hybridized carbocation has a p orbital. Now I cannot continue drawing this mechanism, knowing this reaction, if I draw a structure like this. It becomes difficult. Then I am going to tell suddenly that this structure is same as this. So this alone would freak out people who cannot see this structure in 3 dimensions. How is this similar to this? Those who would know these structures by now would know that everything that I need to do here, let me try to take my pen here and then maybe I'll be able to draw it better. So all I have done here is I would just rotate this molecule like this. So if I rotate the molecule in that direction, again I'll go to the pointer, this carbon atom here where I'm holding my pointer now comes here because I just rotated it downwards. This carbon atom which had the positive charge also is being rotated and it takes up a new position here. This CH2 which is attached to these two are going to come up and it is going to give me this. This bond here which is between two CH2s will also rotate in this direction and it is going to reach here. So that is when I get this structure. So this structure is same as this. All I did is I tilted it. And once I have done that, I have the same structure I have drawn here. So this is the same compound I have drawn here. So let us have a look here. So I got a positively charged species here. There is a carbon hydrogen bond on this. So this is this CH3 where my pointer is currently. And that CH3 means that there are 3 carbon hydrogen bonds. I have shown only one of them. One of these would lose an H as a positively charged proton, as a proton. So then I get a double bond. The moment I get a double bond, this positive charge is gone. The positive charge is now gone as an H plus and I have a double bond. Now all of you know that double bonds would react with electrophiles because double bond is an electron rich species. It is going to react with an electron deficient species. And when acetic anhydride and H2SO4 are mixed, it generates an electrophile which is SO3H, which is protonated sulfur trioxide. I can write a mechanism for the formation of these two, which is a very interesting mechanism. So I will urge all the MSc students or all the students who like organic chemistry to write a mechanism for the formation of this species from acetic anhydride and H2SO4. It's an extremely interesting mechanism, and if you are able to draw that, it would tell you that you understand where you need to protonate in a reaction. So anyway, for the sake of this discussion, to continue this discussion, I would only say that I generated this electrophile here that will react with this double bond and generate a new carbon sulfur bond. And because these two electrons are moved towards the SO3H, a positive charge will be placed on this carbon atom. Now this is similar to this one, except that the H is now replaced with an SO3H. This reaction here is not reversible. So all the other steps in this reaction are reversible. That means it can go in this direction, it can go back and give me camphor. But once this happens, this step will not go by. This carbon-sulfur bond will not break. It is because SO3H is an extremely strong electrophile. It does not want to stay as a positively charged species. So once it reacts forever. And then you get a carbon-sulfur bond and you generate a new positively charged species. Now, if you remember what I said earlier, this positive charge means that I have a p orbital in the direction that I am drawing here with my laser pointer, which is parallel to this particular bond. So this bond comes back onto this and I get a new carbocation. So the bond that I am showing now has broken. A new bond has formed between this carbon and this carbon, which is the one that I have drawn here. This carbon now has a positive charge and an OH group. A positive charge and an OH group means I can use the lone pairs in oxygen and here I have just flipped the structure here. So this is the same structure. All I did is earlier we rotated this molecule in this direction. So here I have rotated back in this direction. So this carbon and OH is coming down. This CH2 is coming down. So this structure is exactly same as this. And then what I do, I use the lone pairs on oxygen and form a double bond here. So the positive charge moves from this carbon to the oxygen now. So it is a protonated ketone which loses an H plus again to give me camphor sulfonic acid. So you see this mechanism. This mechanism can easily be drawn if you just remember a few things. One of them is that the protonation always happens on the electron rich species. And once it has happened, then a carbocation is generated, and the carbocation means an empty p orbital. Now it can start to interact with any electron rich bond which is parallel to the p orbital, and then if you know that much, you will be able to write a mechanism with a little bit of interest in organic chemistry and with a very good understanding of three-dimensional structures, and you will be able to end up drawing this product and write a very convincing mechanism for the formation of this. So let me again go back to that slide. You see you had camphor, you had an SO3H which came over here. Very complex reaction otherwise, because you had 3 CH3s to choose from. You had CH2 groups, but it happens only here because this is the only CH3 which can have a positive charge adjacent to this. So life looks simple once you know this. Not really. Now I have another example here. This is similar to what we had with camphor. In camphor, I did not have this bromine, so I added 2 bromine here. So this is a dibrominated species of camphor. I do that because if I don't do it, as soon as I treat with bromine, bromine will start coming here. So I already start with a molecule which has 2 bromines. These bromines are just put there so that these positions do not start taking up bromine. So you can practically ignore them. But you look at the molecule otherwise, you would see that this is again the same structure as camphor. Now, instead of H2SO4 and acetic anhydride, now I am going to treat this one with bromine, which itself is an electrophile. And instead of sulfuric acid, I use chlorosulfonic acid, which is a stronger acid, but you can also treat it with concentrated H2SO4. You will get similar results, but this one will give you a better yield. So if you take bromine and this one, so I have a different electrophile. Earlier the electrophile was SO3H. Now my electrophile is going to be bromine. Again, I have 3 CH3s to choose from, but bromine chooses this CH3, not this one. And it has 2 CH3s which are similar. On this carbon atom, there are 2. It only chooses this CH3, which is pointing towards these 2 Br groups or the keto group. So imagine organic chemists who did these reactions. They took camphor, they put sulfonic acid and acetic anhydride, they got camphor sulfonic acid, pretty happy. You take this dibrominated compound and do a similar thing with bromine. You would normally expect the bromine to come over here, but the bromine does not come here. Instead, the bromine comes on one of these CH3 groups. Now, the organic chemists have to explain this. You have to say why this happened. Which theory will you use? Which orbitals will you use? Only what you are comfortable with. So let me draw a mechanism for that too. I will rush through this mechanism because I know this is too many mechanisms now. So again, the reaction starts the same way. You have an H plus, it gets protonated here. So those who remember my previous mechanism would know this is a similar step. This bond migrates, I get this positively charged compound. I rotated it in this direction. That is when I got this. From this compound, last time what I did, I took away an H from here and drew an alkene. So from this compound up to this alkene here, I am missing the BRs here on this structure. I'm sorry about that, but assume that these are 2 BRs. Anyway, we get this particular structure here. So this structure is similar to the structure you got with camphor. These two methyl groups are the methyl groups which are here, and there was one methyl group on this position, and that is the methyl group now having this double bond. So up to this structure you got in the previous mechanism. Now what happened there was that SO3H was able to attack on this, and the reaction proceeded. Now once you have this species, what we would expect here is bromine is going to react here, and you should brominate this. Just like SO3H reacted here, bromine should do this. But what happens, unfortunately, bromine is a weaker electrophile. SO3H with a positive charge is a stronger electrophile. SO3H will be able to react with this double bond because it is a stronger electrophile, whereas bromine, which is a much weaker electrophile, will never be able to react with this double bond and generate a positive charge on this center back. Because this, once an electrophile reacts here, you generate a positive charge on the carbon atom here, which is closer to a carbon atom that is attached to an OH group. So as you need a stronger electrophile to generate this positive charge back here, a weaker electrophile cannot do this. So what happens? Therefore, this alkene will only react with the H plus that went out and give you back this one. It will. So H plus here is a stronger electrophile than bromine. So therefore, what will happen? You will get back this species, not a brominated species. Once you get this here, I have this structure here. So this is the same compound here. And in this, I have drawn this p orbital clearly. So this is the empty p orbital. If you look at this p orbital here, this p orbital is parallel to this methyl group. So the methyl group on the back carbon atom, this methyl group and this one are parallel, whereas this methyl group is not parallel. This bond is not parallel to the p orbital. This bond is. So the electrons in this can actually be donated onto this p orbital, and so just like this here, so this methyl group can migrate onto this and give you this species. So that means what happens, this carbon-carbon bond breaks and the two electrons in the carbon atom are going to be given here. So along with that, this methyl group migrates onto this and you get a new positively charged species. So initially you had a positive charge here and the positive charge now moved here, and one of the methyl groups migrated to this. And now once you get that, this positively charged compound again gives you an alkene, and this alkene can react with bromine. The reason is, once this alkene reacts with bromine, you generate a carbocation, and that carbocation is not adjacent to a carbon atom with OH. If you generate the carbocation here, that carbocation is closer to a carbon with an OH, so there is an inductive effect towards this carbon, which destabilizes the positive charge on this carbon atom. Whereas in this carbon atom, there is no such destabilization. So therefore, what happens? This carbocation can form. But once it has formed, this carbocation and this carbocation are similar in energy. Therefore, this p orbital on this carbon is parallel to this methyl. So this methyl again migrates back onto this. See, this mechanism is little complex, so not all of you would be able to follow it very easily. I understand that. But just take me for granted here that this methyl group migrates onto this and you start making up a new positively charged species here. Now this one has resulted in something very interesting. It is always the methyl that is pointed downwards that is migrating. So therefore, when this methyl group goes onto this carbon, this CH2Br is pushed towards these other two Br atoms. And once you generate this positive charge, rest of the things are similar to what happened with camphor sulfonic acid. There is a p orbital here. This bond is parallel to that. So this orbital, this carbon-carbon bond migrates towards that, and you start getting this positively charged species here. This can be rotated again like it did before, and this is the structure. That the double bond can be shifted between these two. So this is the structure. It can lose an H plus and finally give me this compound. Those of you who are good, those of you who are doing advanced organic chemistry in MSc, for example, would have been able to follow the whole thing. And you would be able to see that when I change the electrophile from sulfuric acid to Br2, my Br came on this methyl group instead of this methyl group. And the entire thing can be explained based on the fact that Br2 is a weaker electrophile, whereas SO3H plus is a stronger electrophile. Rest of the things only require you to know the three-dimensional structure of the molecules and the orbitals that are involved, and the fact that an empty orbital can react with an electron-rich orbital, whether it is a bonding orbital or whether it is a lone pair of electrons, and that can result in a rearrangement. That would give me this product, and that would explain this. Now, I know I have taken up enough time here. So this is my last slide here. So I would like to end my last slide with this particular photograph. This photograph was taken by me. This photograph was taken in Vaikam, where I am from. This was taken in an evening while I went out for a walk with my son. And I saw a nice, beautiful sky, and I took this photograph. Now, one of the things that organic chemists are always being blamed by theoretical chemists and theoretical physicists and other chemists who do quantitative science are that we report things without knowing the reason behind it. So I thought I can explain that particular reason why I report a thing without always knowing the reason behind the thing is using this photograph. So when you have observed something, when you've seen something, that is what organic chemists do. We do reactions, we see what has formed, and whatever has formed, we report that. If we can give an explanation based on the available theory, we try to do that. If you do not have a theory that can explain what we have observed, we still report the observation. In cases, least bothered about the reason behind an observation. But we are always excited to see something that is nice. So therefore, an organic chemist is a different character type. A physical chemist or a theoretical chemist is a different character type. An organic chemist is a character type who observes things that are interesting and report them as such. Let me come back to the photo. So I took this photograph, I found it interesting, I found the sky to be very interesting. I take this photograph, I posted it in my Facebook, I have a Flickr account, I posted it in my Flickr account too. I got a lot of comments, lot of likes, people said beautiful photo, nice vivid photo, and they were appreciating my observation, and I am happy with them. Imagine that I also had a theoretical person with me. Let us assume that I had Sheldon Cooper with me while I was there. He would have seen this nice picture. He very unlikely that a Sheldon Cooper, who is a nerd, who is an extremely eccentric physicist, may not have had a camera like I had. He would have probably looked at the photo, looked at this sky and thought about why is it so vivid? Why exactly is the sky having so many colors, so dispersed? He can easily come up with an explanation because he knows that the sunlight gets scattered during the evening and that results in all this. So now if he has a Facebook account, he would probably go into his Facebook account and write that this evening I was walking with Ramesh and I saw this nice, beautiful sky. It was vivid and I know why it was vivid. It was because the light was getting scattered for so and so reasons. So now somebody reads his post, they would be happy with the explanation. They would start giving him likes. Somebody sees my photograph, they are happy with the photo I posted, they would give me likes too. But some of the people who have seen Sheldon Cooper's post about the reason why the sky was very vivid would probably ask him, what sky are you talking about? When you said the sky was vivid, then what he could write is, oh, you go and see Ramesh's Facebook post where there is a photo of it. He is the one who observed it, he is the one who took the photo, and the photo is there in Facebook. So he comes to my account and he would see the photo. Then he takes Sheldon Cooper's explanation. He would be able to say why the whole thing happened. Be somebody who sees the photo in my Facebook post and wonder, why is the sky so vivid? He would find an explanation in the theoretical person's Facebook page where a reason behind the vividness of the sky will be explained. Combining these two, you actually have an observation and the reason for this. So what I mean to say is the person who observes a nice thing do not always have the responsibility to express it, to explain it. The explanation can be given if it can be explained. But he should not shy away from reporting his observations just for the reason that he does not have a proper explanation with him. Experimental chemistry, experimental organic chemistry is always about carrying out reactions and designing reactions with the purpose of having new observations. Explanations might follow. If they are satisfactory, we are happy that an explanation can be given. And we are always ready to accept very good explanations for the observations that we have. we never undermine people who give reasons for everything. We need those reasons. But please understand, those who think that organic chemistry is only about reporting things without an explanation, or is only about mugging things, if you start taking up a career in organic chemistry because you could mug up, very soon you start performing very badly in competitive exams. You will start performing very poorly in organic chemistry, because organic chemistry is always about observing a structure in space and understanding the structure of organic molecules. And that requires that you have a vision which gives you three-dimensional structures and somewhat an idea about how an hybridized orbitals would look. And you need to remember that some of the orbitals would be electron rich. They will interact with electrons. If this much is known, you would start to write mechanisms better. You would start to realize that the extent to which you need to mug up has become less. You study 1,000 named reactions. There are around 250 named reactions that are most commonly used. You study all of them. Still, you will not be able to write a mechanism for camphor becoming camphor sulfonic acid if you do not know how to explain it with the three-dimensional structure of an organic compound. With this, I'll stop my talk here. Dr. Ranimol had also asked me to give a brief discussion on my research that I do, but I realized that that will be totally out of place during the course of this talk. So I'm stopping it right now here, and I thank all of you wholeheartedly, and for those who are listening to me through the seminar, thank you very much.
Okay. Thank you so much, sir, for your energetic, excellent presentation. Okay.
So I think I should stop presenting now, right? Yeah. Okay, fine. Yeah. Thank you very much, all of you. So I hope people follow.
Okay. Next, let me move on to the question answer section. If anybody have any questions, they can type your questions in the chat box. Okay. Sir, shall I read your question?
Okay, yeah, sure. If there are anything that I could answer.
Somebody comments are there. Nice presentation, excellent, very interesting, creative explanation. Okay. How the non-classical carbohydrate intermediate affect the unusual behavior of bicyclic compounds?
Okay, so first of all, let me tell you that, see, this, I can clearly see that this is an organic chemistry student, probably doing first year MSc and having trouble with seeing all these non-classical structures, doing all sorts of rearrangements. Okay, so let me tell you this. A non-classical carbocation simply means that you have a carbocation and you have a bond with electrons adjacent to this positively charged carbocation, and these bond electrons are somehow interacting with the empty p orbital on a carbocation. Now it requires, for this non-classical carbocation to form, what is required is that the empty p orbital and the bond that is involved should be parallel to each other. So once you can see this much, then what happens is this bond electrons, the electrons in the bond. So the bond can be a double bond, it can be a single bond. These electrons and the empty p orbital, they will start to interact. So all together, you will have three atoms there. Two atoms which are forming the bond, and the third atom, third carbon atom, which is having the positive charge. So these three atoms have two electrons, which are the electrons in the bond. So what you really have is a 2-electron 3-center bond. And this 2-electron 3-center bond is what you call as a non-classical carbocation. And once you have this non-classical carbocation, the reaction can proceed in such a way that a new bond is formed, and one of the carbons which had the positive charge should get back with whatever nucleophile is attacking, that will attack on this. So that results in the rearrangement. So realize that every non-classical carbocation that you are talking about is a 3-atom, 3-carbon, 2-electron bond. And all these three are equally involved with these 2 electrons. And one of those carbon atoms would get the nucleophile. The bond will be formed between the other 2 carbon atoms. And that results in this. I hope I am clearing this.
The next question, what is the role of antibonding orbital of living group?
Okay. So this is something that we learn, and even in +2, some of the students start asking this question. When you have a carbon-bromine bond, a CBr bond, Br, the bromine atom is the most electronegative, much more than carbon. But then why does the nucleophile attack the bromine atom, carbon atom? Why can't the nucleophile just attack the bromine atom and then form a nucleophile bromine bond rather than a carbon nucleophile bond? So what happens here is that when you have a carbon bromine bond, we always know that the bonding orbital between carbon and bromine here is not symmetric. It can actually be written in such a way that the electrons are more towards bromine. That means if I take localized bonding orbitals of carbon-bromine bond, the bonding orbital is asymmetric because bromine has a higher coefficient in the bonding orbital and carbon has a higher coefficient in the anti-bonding orbital, which simply means that when I draw a CBr bond, the carbon atom has a delta positive charge and Br has a delta negative charge. And because carbon atom has a delta positive charge, in molecular orbital terms, it simply means that the anti-bonding orbital of carbon-bromine bond has a higher lobe on carbon atom and a smaller lobe on bromine atom. So therefore, the nucleophile, which is an orbital with electrons, would like to interact with the bigger orbital, which in this case is the carbon component of the CBr anti-bonding orbital. And this anti-bonding orbital of CBr is always oriented opposite bond. And that is the reason why the nucleophile goes and interacts with the anti-bonding orbital and gives you a new bond in that direction. So in order to have this explanation better, you need to understand what an anti-bonding orbital is or why anti-bonding in orbital of CBr is important. One more point just related to this, you would have also learned that when you learn about the reactivity of nucleophiles, you learn this thing that O minus is a better base and S minus is a better nucleophile. So if you go down the group from oxygen to sulfur, a negatively charged oxygen is a better base and a negatively charged sulfur is a better nucleophile. Why is it so? So remember this thing that nucleophilicity is a reaction of an electron-rich orbital with an electron-deficient orbital, which in this case is the anti-bonding orbital of carbon. So in sulfur, you have a more diffused orbital. So the electron-containing orbital of sulfur is more diffused. So it has a better chance of interacting with the anti-bonding orbital of carbon, carbon-Br bond, than the more centered orbital of an O minus. Whereas once it comes to the reaction with H plus, that is what basicity is. So instead of a carbon, if it is reacting with H plus, which is also a point charge, would react better with oxygen minus, with the orbitals of oxygen, because it gives you a more stronger bond. So in short, basicity is a thermodynamic behavior, whereas nucleophilicity is a kinetic behavior. And a kinetic behavior would be faster if you have more diffused orbital, and a thermodynamic property, a thermodynamic reaction, a reaction under thermodynamic control would be better if the net energy of the reaction is more favorable. That means you are able to form a stronger bond. And that is the reason why basicity is more for O minus and nucleophilicity is more for S negative, S minus. So all these things can be explained if you just look into the orbitals that react. And if you know that, you don't have to by heart. You just need to know which orbitals are reacting. Thank you.
Okay, sir. Another question from Anjana K.R. Is there any possibility of alkyl shift based on carbonium ion stability after the nucleophilic attack in first reaction?
Yes. So if you look at the camphor mechanism that I wrote, I drew that in the second case where the bromination was happening. There was a methyl group that was migrating. So methyl group is an alkyl group. So what you really saw there was an alkyl group migrating. It was a methyl group, it could have been an ethyl group, it could have been a benzyl group and so on. So alkyl groups will migrate provided the carbon alkyl bond that we are talking about is parallel to the p orbital having no electrons. So the positively charged atom has a p orbital. If there is an alkyl group bonded to an adjacent carbon atom, and if that carbon bond is parallel to the p orbital, it migrates.
Sir, do you have any advice to the students who are preparing JAM examination?
Okay, so when you, I know that as a BSc student, I did my BSc from Kerala. So while I was studying in one of the colleges, I learned that I was again learning a lot of reactions, just like the way we did +2. And then at the end, I know a lot of reactions. And then but once you start writing exams, you would realize that knowing the reactions alone is not going to help you, because with the same set of reactions, if you will understand, even if you know the reagent, you will not be able to write reactions if you do not know the structure. So in IITs, what we do is all our organic chemistry courses right from the graduate level, from BSc, starts with stereochemistry. So the reason why we do that is understanding stereochemistry and structure of organic compounds is more important to do better in organic reaction mechanisms or organic reactions. So those of you who have been learning reagents and knowing a lot of reaction, you need to start looking at stereochemistry in detail and learning about stereochemistry of organic compounds and start looking at structures in space. Unless you are able to do that, it would become difficult, especially in answering questions in a competitive exam, because most of these questions are prepared by organic chemists who are from IITs and so on. So they put a lot of emphasis on understanding the structure properly. Yeah,
Okay.
I think that is what you should do.
Okay. Then the question answer section is over.
Okay, thank you.
Next, I call upon Dr. Ranimon Stephen for giving vote of thanks. Ranimon Stephen, Dr. Ranimon Stephen, over to you.
Excellent presentation, Dr. Ramesh. We got a lot of comments like you are one of the best organic chemists in India. Thank you, Dr. Ramesh. It was an excellent and a very informative session. So now I move on to my duty. So, respected Principal, Dr. Sabu K. Thomas, Vice Principal, Reverend Father Anto N.J., our guest of the day, Dr. Ramesh Ramapanicker, Head of the Department, Dr. Tanya Francis, teachers and participants from various colleges and institutes. Good evening to all. COVID-19 is playing havoc in our personal and professional lives. Due to COVID-19, all academic activities across our country have gone online. As it is not certain when this pandemic will be over, it is important to accept the new norm and get on with our business as usual. The only positive thing that has happened due to COVID-19 is that it has brought people who are far away nearer to us. The webinars has brought us together, which otherwise would not have been possible. As you are aware, we, the teachers of Department of Chemistry, initiated a series of webinars, and today is the concluding day of that series. We are happy that all the webinars were well attended and the participants benefited from the talks and discussions as evidenced from the feedbacks obtained. On behalf of Department of Chemistry, St. Joseph College, Devagiri, I take this opportunity to propose vote of thanks to those who have contributed to this webinar series. At the outset, I thank today's resource person, Dr. Ramesh Ramapanicker, for accepting our invitation. He was very busy on these days because three of his students are going to submit thesis. In spite of his busy schedule, he accepted our invitation. And thank you, Dr. Ramesh, for your highly informative talk. I am sure that the participants have benefited from this talk. Thank you, Dr. Ramesh. I also wish to place on record once more our gratitude to the earlier speakers, Professor Sabu Thomas, Vice Chancellor of University, Dr. Shishir, University of Amsterdam, and Dr. Omya Agustin from University of Qatar. I would like to thank our principal, Dr. Sabu K. Thomas, for his enthusiastic support during all the webinars. Thank you, sir. We are thankful to the manager, Reverend Father Bindu Joseph, and Vice Principal, Reverend Father Ando Ente, for all the support and motivation to conduct this webinar. Thanks to Head of the Department, Dr. Tanya Francis, and all teachers in the Department of Chemistry for their unflinching support and help. A special thanks to my co-coordinator, Dr. Soumya Varghese. This series of webinars would not have materialized without the immense help of Dr. Jomon Matthew, who worked very hard behind the scenes. Heartful thanks to Dr. Jomon Matthew. I would like to thank our computer center and library staff for providing the facilities and technical support. I would like to acknowledge the financial support of DBT staff in conduct of this series. Our heartfelt thanks to all the participants, teachers, and students from various institutes in India and abroad for their active participation. We hope to see you all in our future webinar series. Thank you. Thank you all.
The webinar is over now.